Hi class, this is Mr. Morris, and we're going to talk about ionic solids in this video. Last video talked about covalent bonds, so naturally we go on to ionic bonds next. To the right, you see a diagram of the crystal lattice of NaCl. We can kind of look at this, and it wants us to identify, the question asks, to identify which ion is Na plus, which ion is Cl minus. We need to stop and think about that for a minute based on what we know from the periodic trends topic from last unit. All right, pause the video if you haven't already answered it. The way that we need to think about this is by comparing the size of the ions. Their ionic size or their ionic radius. Na plus has two energy levels. If you were to look at it on the periodic table, Na is in the, I believe it's in the third energy level, but when it loses an electron, it has two energy levels. Cl has three energy levels. So which one would be bigger? Chloride ion would have a larger radius than the sodium ion, and that is why we can identify the purple one is sodium and the green ion is the chloride ion. When an atom loses an electron, like Na, we want to identify what type of process this is. So thinking back to what we learned last time, if an atom loses an electron, is that endothermic or exothermic? That is an endothermic process for an atom to lose an electron. When an atom gains an electron, like chlorine gaining an electron to become chloride, that would be an exothermic process. All right, we want to label these reactions with a delta H value that makes sense, that matches up. Again, delta H is going to indicate whether it's endothermic or exothermic. An endothermic process has a positive delta H. An exothermic process has a negative delta H. By the way, I'm going to go through these questions with you. In the future, you'll want to be able to answer them on your own. And if you feel like you can answer it anyway, pause the video, check the answer, and see how you did. So sodium becoming a sodium ion and giving off an electron, well, that is a positive delta H. It's an endothermic process for sodium to give off an electron to become a positive ion. And chlorine, when it gains an electron, it releases energy. It forms the attraction. It's an exothermic process, so that would have a negative delta H. Now let's see if we could label the next two. We've got a positive number, we've got a negative number. So which one is positive and which one is negative? All right, so remember, over here we are breaking a bond, making ions, and over here we have ions, we're making a bond. Which one is endothermic, which one is exothermic? Breaking a bond is endothermic and forming a bond is exothermic. So that's why we select a positive delta H for sodium chloride breaking apart into ions, and we have a negative delta H for the ions coming together to form sodium chloride. In the first reaction, the ionic bond is broken. In the second one, and that's an endothermic process, and in the second reaction, an ionic bond is formed. This is an exothermic process. Now let's talk about lattice energy. Lattice energy is the amount of energy released when 1 mole of ionic compound is formed from its gaseous ions. So we've got this picture over here that shows a bunch of gaseous ions, sodium ions and chlorine ions, snapping together to form an ionic compound. When they do that, it releases some heat. It releases some energy. That's called the lattice energy. The higher the lattice energy, the greater the strength of the ionic bond. So if we have a very strong ionic bond, it's going to have a high lattice energy. This leads to higher melting points and higher boiling points as well. If you've got a strong ionic bond, you have high lattice energy, you're going to have a very high melting and boiling point, which means it's hard to break those bonds. Consider Coulomb's law. Energy equals a constant times Q1 times Q2 divided by R. For ionic compounds, Q1 and Q2 represent the charges of ions, like a positive ion and a negative ion in this example. You've got your positive chlorine, or I'm sorry, your positive sodium and your negative chloride ions. The R represents the distance between the nuclei of the ions. Now, if you look at this, it looks like they're pretty close to each other in a solid. For a given arrangement of ions, the magnitude or the value of the lattice energy increases as the charge of the ions increases, or as the distance between the nuclei of the ions decreases. So the lattice energy can increase either because we have a stronger charge or because we have a smaller distance between the ions. Those are two ways we could have a greater lattice energy. The distance between the nuclei of the ions are influenced by the radii of the ions. So the ionic radius or the atomic radius. The distance between nuclei of an Na plus ion and a Cl minus ion is equal to the radius of Na plus the radius of Cl minus. This picture kind of indicates, or it's a visual for that. The radius of chlorine is the distance from the center of the atom to the edge of the atom's electron cloud, of the ion's electron cloud. And then for sodium, same thing, from the center to the edge of its electron cloud. So if we wanted to find the distance between the nuclei of these two atoms, we would measure the radius of each and then add them together. Note that the magnitude of the lattice energy depends mainly, it says predominantly, that means mainly on the ionic charges, because the ionic radii vary only over a very limited range. To evaluate ionic bond strength, you always compare ionic charge and ionic radii. We first always compare ionic charges. That's your number one thing, is see if the charges are the same or if they're different. If they're the same, then we look at radius. So this question asks us to explain why CaO has a greater magnitude in lattice energy than NaF, which has a higher melting point, CaO or NaF. So it says to explain why it has a greater magnitude of lattice energy than NaF. Well, we can compare these two and look at a couple different things about them. In CaO, the ionic charges are +2 and -2. So the magnitude of the charge is +2 and -2 for CaO. In NaF, the ionic charges are +1 and -1. We can see that the higher ionic charges in CaO would lead to a stronger Coulombic attraction and the greater magnitude of the lattice energy. If I have +2 and -2, they attract each other more strongly. That gives us the higher Coulombic attraction and the greater magnitude of lattice energy. Therefore, the melting point of CaO will be greater than the melting point of NaF because it takes a higher temperature to break the ionic bonds in CaO because of that stronger attraction and the greater lattice energy. All right, in this one, we're explaining why lithium chloride has the greatest magnitude and lattice energy and why CsCl has the lowest magnitude in lattice energy. Which compound has the lowest melting point? So as we compare these, they each seem to have the same charges, +1, -1, +1, -1, +1, -1, +1, -1. So we've got to compare something else. Since they all have the same ionic charges, we need to compare their radii. Li has a smaller ionic radius than Cs because Li has only one energy level. If we looked at the periodic table, we could see that it's in the second energy, that lithium's in the second period, but if it loses one electron, it would have only one energy level. But Cs in the sixth period, but after it loses one electron, it has 5 energy levels. Well, it's still much, much larger than lithium. So cesium has the biggest ionic radius, lithium has the smallest ionic radius. The distance between the nuclei is smaller for LiCl than for CsCl, or for any of the others in this list, for that matter. So the Coulombic attraction is stronger for LiCl and it's weakest in CsCl. The lowest melting point will be CsCl because it has the weakest attraction, the least energy needed to break those intermolecular forces apart. Or in this case, because we're talking about an ionic solid, to break apart the ionic bonds. All right, we want to arrange LiCl, KBr, and MgCl2 in order of increasing melting point and justify our answers. In LiCl, we have a +1 and -1 charge. In KBr, we have +1 and -1 charges. And in MgCl2, we have a +2 charge and -1 charges. So MgCl2 has the highest melting point because of magnesium's +2 charge. It has a greater charge, a stronger attraction. The radius of K plus is larger than the radius of Li plus, and the radius of Br minus is larger than the radius of Cl minus. So it would stand to reason that KBr is going to have a larger radius than LiCl. As a result, LiCl is going to have a stronger ionic attraction. The lattice energy will be less for KBr or more for KCl, and the melting point for KBr will be lower, and the melting point for LiCl will be greater because there's a stronger lattice energy for LiCl. It makes the melting point larger for LiCl as well. The melting points in increasing order, which is what this question asked for, would be KBr, and then LiCl, and finally MgCl2 for the reasons that we listed above. All right, some properties of ionic compounds. Ionic compounds have high melting points and high boiling points due to the strength of the ionic bonds. Ionic compounds do not conduct electricity in the solid form, but ionic compounds conduct electricity in the liquid form. They also conduct electricity in aqueous solutions when they're dissolved in water. We've talked about that briefly, and I think it showed up on the Unit 0 test. But you do need to know these facts about ionic compounds. They don't conduct electricity when they're solid, but they do conduct electricity in the liquid or aqueous form. In solids, and this is an explanation of why, in solid form, ions are fixed in place. They can't freely move around, so the ions cannot conduct electricity. In the liquid or aqueous form, the ions can freely move, so the ions can conduct electricity, and they do. We've got a picture here. This is the ionic solid. It cannot conduct electricity. So if you were to just put a light bulb tester and put the electrodes into, say, just a pile of salt, it's not going to conduct electricity. But if we have a liquid salt, or if it was dissolved in water, then it will conduct electricity because those free ions can move around. Also, we know that ionic crystals are hard, they're rigid, they're brittle. These crystals can often be cleaved. That means they'll break apart across or along smooth, flat surfaces. So when we say they're brittle, they break pretty easily, and they break apart and crumble if you were to try to smash them. This image kind of explains why. As external force, like this hammer here, is applied to the ionic crystal, the planes of the atoms slide past each other in response to the stress. The repulsive interactions between the like charges, looking at this second picture, the like charges, as we move the atoms down a little bit, the like charges will line up, and that repulsion will lead them to separate like this, and then we break off into different layers. This leads to the brittle nature of ionic compounds. And that's it for the ionic bonds. Next time we're going to talk about metallic bonds.